Hello, everybody. In this video, we are going to continue our discussion about linear higher order ordinary differential equations. And we are going to consider now homogeneous linear equations with constant coefficients. So our coefficient functions are constant functions. We have n constants, a1, a2, an. And since we consider homogeneous equations, the right side of our equation is going to be 0. a1, a2 up to an are constants, real constants. Remember, our differential equations always about real valued functions. We may have to use complex numbers when we are trying to solve the equation, but at the end, our solutions are always real valued. So we take real constants, a1, a2, up to an, and our equation, nth order, so y at the nth derivative of y plus the constant a1 times n minus first derivative of y plus we go up to an times y and we take it equal to 0 because we are considering homogeneous equation. Now remember, we convert such an equation into a system. So the corresponding system is we take x1 equals y, x2 equals y prime, and xn equals the n minus first derivative of y. So the system is, remember, if we take the vector function of x1, x2 up to xn, then we have the system derivative of x with respect to t equals the matrix A times x, where our matrix is 0, 1, 0, 0, 1. And in the last row, we have minus an minus an minus 1. We go like this, and the last one is minus a1. And since we consider homogeneous equations, we don't have the plus b part in our system. The vector b is 0. The vector b is 0. All right, now how do we find solutions of such a system? Remember, we discussed solutions of systems before. So we need to write the matrix A in a more simple form. If it's diagonalizable, we write it in diagonal form. If not, in general, we write it in the Jordan form. So if the matrix J is the Jordan form of the matrix A, remember J may be diagonal. This includes, the Jordan form is the most general form. It includes the diagonal case. Then this means, remember, we can write the matrix A as some matrix P times the matrix J, P inverse. And remember how we obtain the matrix P. If it has columns V1 up to Vn, the columns Vi's are eigenvectors or generalized eigenvectors in case of repeated eigenvalue, generalized eigenvectors of A. Now, once we find this matrix P and the Jordan form J, then a fundamental matrix of the system is, remember, we denote fundamental matrix by the Greek letter C. So we can find our fundamental matrix by multiplying the matrix P with the matrix exponential of the matrix J. And fundamental matrix means columns. Remember again, this is all recall from the theory of systems. Columns of the fundamental matrix are solutions, independent solutions of the system. So we write our fundamental matrix, and columns of the fundamental matrix are solutions of the system. And remember, once we get the solutions of the system, the first component of each solution gives us a solution of the original differential equation, nth order differential equation. Now, how do we find this matrix P? To find the matrix P, we start with finding eigenvalues of the matrix A. So to find eigenvalues of the matrix A, we consider the equation the determinant of the matrix A minus lambda times the identity matrix equal to 0. Now, our matrix A has this special form. You see it above. We are going to get a formula for this determinant. For the matrix A, we obtained by converting our differential equation into a system. So first, let's consider the case n equals 2. For n equals 2, the matrix A is 0, 1, minus A2, minus A1. So that the determinant of A minus lambda I is the determinant minus lambda 1 minus A2 minus A1 minus lambda. So this is minus lambda times minus A1 minus lambda minus A2 So this is lambda squared plus A1 lambda plus A2. Remember the constants A1 and A2 comes from the original ordinary differential equation is the second derivative of y plus a1 times y prime plus a2 times y equal to 0. So the constants a1 and a2 are the coefficients of our original differential equation. So once we have those coefficients, the corresponding determinant for the matrix A turns out to be lambda squared. So notice the correspondence between the original differential equation and the polynomial for eigenvalue lambda. Now what happens, let's look at one more case. What happens when n equals 3? Then the matrix A has the form 0, 1, 0, 0, 0, 1, minus A3, minus A2, minus A1. So our original differential equation is the third derivative of y plus A1 times second derivative of y plus A2 times first derivative of y plus A3 times y equal to 0. Then the determinant of A minus lambda I is the determinant minus lambda 1, 0, 0 minus lambda 1, minus A3, minus A2, minus A1, minus lambda. So to expand this determinant, we can use the first row, minus lambda times the determinant minus lambda 1 minus A2 minus A1 minus lambda. Then the next term has a minus sign, minus 1 times the determinant 0, 1 minus A3 minus A1 minus lambda. So this is equal to minus lambda times minus lambda times minus A1 minus lambda minus minus A2, and then minus 0 minus minus A3. So both determinants have a minus sign, so let's take this minus sign out. Then lambda times lambda squared plus A1 lambda plus A2, and then plus A3. So we have minus lambda cubed plus A1 lambda squared plus A2 lambda plus A3. So again, note the correspondence between the terms of the differential equation and the terms of the determinant. Okay, we have a minus sign, but since to find the eigenvalue, we are going to set this equal to 0, the minus sign is not going to affect the solutions. So, of course, it is not enough. We just looked at the case n equals 2 and n equals 3. It looks like we have a correspondence between the coefficients of the differential equation and the coefficients of the determinant of A minus lambda I. I'm not going to provide the details here. For those of you who are familiar with the mathematical induction, you can try using that. So using mathematical induction, we get, for the general case, for general n, the determinant of a minus lambda I, we are going to have, for n equals 2, there was no minus sign. For n equals 3, there was a minus sign. So in general, it's going to be minus 1 to the n, lambda to the power n, plus a1 times lambda to the n minus 1, plus a2 times lambda to the n minus 2, plus an. So again, let me remind you the original differential equation. The nth derivative of y plus a1 times n minus first derivative of y up to an times the function y equal to 0. Oops. Oh my. One moment. Okay. So this part, to get the eigenvalues, we set this determinant equal to 0. So the sign, plus or minus sign, is not going to affect the solutions. We consider this polynomial, we call it Pn of lambda, n for the degree, lambda to the n plus a1 lambda to the n minus 1 plus up to an. This polynomial, the equation. The equation, this polynomial Pn lambda equals 0, is called the characteristic equation of the differential equation of the original differential equation. Okay. Now, roots or solutions of this equation gives us the eigenvalues. And depending, there are several possibilities here. We may have some real eigenvalues, some complex eigenvalues, some repeated eigenvalues. So depending on the case, the solutions, the form of the solutions are going to be different. So we start by considering different cases. And remember, the easiest case, the first case we always consider, is the case of distinct eigenvalues. So that means the equation Pn lambda equals 0 has n distinct roots. Lambda 1, lambda 2, up to lambda n. In this case, these are, remember, eigenvalues of the matrix A. And since we have n distinct eigenvalues, corresponding eigenvectors, say V1, Vn, are independent, linearly independent. We form our matrix P by taking those eigenvectors as columns, and the Jordan matrix, the Jordan form of the matrix A in this case is in fact diagonal with the eigenvalues on the diagonal. And in this case, we know that the matrix exponential is again the diagonal matrix e to the lambda 1t, e to the lambda 2t, and e to the lambda nt on the diagonal. Again, we have done this before when we consider the systems. So this is our matrix exponential of the Jordan form. A fundamental matrix, then the matrix P times the matrix exponential. So the eigenvectors times the diagonal matrix e to the lambda 1t, e to the lambda nt. So when you multiply this out, the columns are e to the lambda 1t times v1, and the last one, e to the lambda nt vn. Independent solutions of the system are just the columns of this fundamental matrix. So the first one is e to the lambda 1t times the vector v1, and the last one, e to the lambda nt times vn. Now, to find solutions of the differential equation, remember, we take the first component of the solutions of the system. x1, x2 up to xn, these are vectors. So x1, xn are vector functions. First components, let's say, first component of each vector function are the independent solutions of the original differential equation. Because of the special form of the matrix A, each eigenvector has a non-zero first component because of the special form of the matrix A. Each eigenvector has a non-zero first component. Again, I'm not going to go into the details. So the first components are going to be non-zero multiples of the functions e to the lambda 1t, e to the lambda 2t, e to the lambda n t. So these functions e to the lambda 1t, e to the lambda 2t, e to the lambda n t gives a basis for the solution space of the original differential equation. Now, this case includes the case of having complex eigenvalues because the matrix, our matrix A is a real matrix. So if it has a complex eigenvalue, the complex eigenvalues are going to come in pairs of conjugates. So if there is a complex eigenvalue, lambda, let's say, so it's a complex number of the form a plus I times b. Here, a and b are real numbers, and I is the imaginary number whose square is -1. So if there's a complex eigenvalue, then its complex conjugate, lambda bar, remember, which is a minus I times b, is also an eigenvalue. And remember, in this case, how we write the corresponding solutions is also an eigenvalue. A corresponding solution, we need to consider, again, e to the lambda t. So e to the a plus ib times t, e to the at times e to the I times bt. Remember, a and b are real numbers, so e to the at is the usual exponential that we know of. And again, recall that when we have the I, it means the complex number cosine of bt plus I times sine of bt. So, of course, this is a complex solution, but remember, we also have the corresponding, we also have the complex conjugate of the solution. And from this one and its complex conjugate, remember, using the principle of superposition, we obtain the real solutions. We take the real and imaginary parts of the solution. So the real part, e to the at times cosine bt, and the imaginary part, e to the at times sine bt. So for a complex eigenvalue, we get two real solutions because every complex eigenvalue comes with its complex conjugate. So in fact, we have two eigenvalues, and we get two real valued solutions. So we can regard the case of having complex eigenvalues we can regard it as a part of the case where eigenvalues are distinct. Okay. Now let us consider some examples. Now let's start with a simple example. Solve the equation the second derivative of y minus the function y itself equal to 0. Now, once we obtain the form of the solutions, we are not going to go back into the system anymore. Using the system, we obtain the numbers lambda, we obtain the characteristic equation, and the roots gives us the eigenvalues of the matrix A. So we are not going to consider the matrix A anymore, just use the characteristic equation. Remember, what's the characteristic equation? For the second derivative of y, we have lambda squared. Plus, for the first derivative of y, but there is no term here with the first derivative of y, so we have 0 times lambda. We can take that the coefficient of the first derivative of y is 0, plus the coefficient of the function y itself equal to 0. So the characteristic equation is lambda squared minus 1 equal to 0. So, of course, the solutions, lambda squared is equal to 1. So lambda is plus or minus 1. We have two distinct roots. Lambda 1 equals 1 and lambda 2 equals minus 1. So corresponding solutions e to the 1 times t and e to the minus 1 times t. Since lambda 1 and lambda 2 are distinct, the solutions are e to the t and e to the minus t are independent. We have a second order equation. We have two independent solutions. So the general solution y is c1 times e to the t plus c2 times e to the minus t. And here c1 and c2 are real numbers. Again, let me repeat, we have a second order equation. So its solution space has a basis consisting of two functions. And here the two functions, in case of distinct eigenvalues, the elements of the basis are obtained by taking e to the lambda t's. So we have two lambdas here, plus 1 and minus 1. So we have two functions, e to the t and e to the minus t. And these are the independent solutions. So the general solution is just a linear combination of these independent solutions. Okay, so maybe to see what to do in case of complex roots, we can consider another simple example. Instead of minus 1, what if we take plus 1? The second derivative of y plus y equal to 0. Then the characteristic equation is lambda squared plus 1 equal to 0. So lambda squared equals minus 1. In this case, we have the complex solutions plus or minus I. Um, so it is enough to consider just one eigenvalue. For lambda equals I, we need to consider the function e to the I times t. This means cosine t plus I times sine t. So real solutions are cosine t and sine t. They are independent. So in this case, our general solution C1 times cosine t plus C2 times sine t. Of course, in this case, our complex solutions doesn't have any real part. So in front of cosine and sine, we don't have any exponentials, just cosine function and the sine function. So maybe we can consider another example where we also have the real part of the complex solution. So example 3, again the same question. Solve the equation. Second derivative of y plus the first derivative of y plus y equal to 0. So again, we consider the characteristic equation. Lambda squared plus lambda plus 1 equal to 0. So to find the solutions, we can use the quadratic formula. Lambda is equal to minus 1 plus or minus square root of 1 minus 4 divided by 2. So this is minus 1/2 plus or minus. This is minus 3, so I times square root of 3 over 2. So the complex roots, the first one is minus 1/2 plus I times square root of 3 over 2. And the second one is lambda 1 bar, complex conjugate, minus 1/2 minus I times square root of 3 over 2. So if you look at the function e to the lambda 1 t, this is e to the minus 1/2 plus I times root 3 over 2 times t. So e to the minus 1/2 t, e to the I root 3 over 2 times t. So e to the minus t over 2 times e to the I times this is cosine of root 3 over 2t plus I times sine of root 3 over 2t. So the real solutions, the first one, we take the real part, e to the minus t over 2 cosine of root 3 over 2t. And for the second solution, we take the imaginary part, but the imaginary part also have this exponential. This exponential is multiplied with both cosine and sine. So the second one also have the same exponential, e to the minus t over 2 times now sine of root 3 over 2t. And the general solution y equals c1 y1 plus c2 y2. So we can, since both y1 and y2 have the exponential piece e to the minus t over 2, c1 times cosine root 3 over 2t plus I times sine root 3 over 2t. Oops, not I. Sorry, c2, of course, c2 times sine of root 3 over 2t. Here, c1, c2, again, can be any real number. Okay, now I want to show you just one more example. It's a simple enough equation. So all my examples until now is of second order, so that the characteristic equation is a second degree polynomial. We can find the roots using the quadratic formula if necessary. Now, if you have a higher order equation, the corresponding characteristic equation is going to have a higher degree. So to find the roots of that equation may become more complicated. If you have, again, real roots, you can try to factor out your polynomial to get your real roots. But when you have complex roots, if it's a more, complicated polynomial, of course, it may not be easy to find the roots. But for some simple cases, we can still find the roots even if the degree is higher. So as an example, let me consider the equation. The fourth derivative of y plus y is equal to 0. Oops, I'm sorry. Okay. So we consider the characteristic equation. Lambda to the 4 plus 1 equal to 0. So this means lambda to the power 4 is going to be minus 1. So this means there are no real solutions. But the degree of the polynomial is 4. So that means we have 4 complex solutions. Remember, complex solutions comes in pairs. So we are going to have lambda 1, lambda 2, and their conjugates. Lambda 1 bar, lambda 2 bar. Okay, now, how to find those solutions? The degree is 4, so we are looking for complex numbers whose fourth degree is equal to minus 1. This is a general problem. It is called finding, so to solve this equation, lambda to the 4 equals minus 1, we need to find fourth roots of minus 1. They are going to be complex numbers. Okay. I want to explain a geometric method to do this. This you can apply to any root of minus 1. In fact, it can be generalized to any root of any complex number, but we are just here going to concentrate on the roots of minus 1. Okay, So remember that when you have a complex number, a plus I times b, here a and b are real numbers, we can consider our complex number as a point in the xy plane. We take the x coordinate as the number a and the y coordinate as the number b, and the complex number z we can consider as a point in the xy plane. And if we look at the distance from the origin to the number z, remember that distance is called the modulus of the number z, and then here we have the angle theta. And now for the number z equals -1, the real part is -1. There is no imaginary part. So as a complex number, we can consider the point -1 in the x-axis like this. So if you look at the modulus is going to be 1. And if you consider this, this angle theta, it is the angle pi. So what we do is as follows. We are looking for fourth roots of -1. So we are going to take fourth roots of -1. So we take this angle of -1, which is pi, and divide it by 4. So we get pi over 4. And okay. And the modulus of -1 is 1. So in the xy plane, we consider a circle. Imagine that this is a circle. So this is a circle of radius 1. In this circle, consider the angle pi over 4. Look at the point where this line of angle pi over 4 intersects the circle of radius 1. This is going to be our first root, lambda 1. And then we are going to get the other roots on the circle again, but we need to change the angle. Basically, to get other roots, add. So the full revolution is 2 pi. Since we are looking for the fourth roots, we divide 2 pi by 4. So we get pi over 2. So add pi over 2 to pi over 4. To get what? 3 pi over 4, right? So we add pi over 2. So we get the second root, lambda 2. And we add another pi over 2. We get the third root. And another pi over 2. We get the fourth root. Okay, so this is this line. This is one line. It is perpendicular to this line. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Oops. Okay, so what are these numbers? Now the angle is pi over 4. The radius of your circle is 1. So lambda 1 is, since the radius is 1, times cosine of pi over 4 plus I times sine of pi over 4. Think about it as polar coordinates. Pi over 4 is your angle. So the x-coordinate is cosine of pi over 4, since the radius of your circle is 1. And the y-coordinate is sine of pi over 4, So as a complex number, we consider the x coordinate plus I times the y coordinate. So this is root 2 over 2 plus I times root 2 over 2. And similarly, the number square root of 2 over 2 is going to be the same for the others, but we need to take the appropriate plus or minus signs. So what is lambda 2 in this case? For lambda 2, it has a negative x component and positive y component. So minus root 2 over 2 plus I times root 2 over 2. Lambda 3 is in the third region, so third quadrant. Both x and y are negative, minus root 2 over 2, minus I times root 2 over 2. And note that this is the complex conjugate of lambda 2. And the last one, lambda 4, is in the fourth quadrant, so positive x, negative y. Root 2 over 2 plus minus I times root 2 over 2. So this is the complex conjugate of lambda 1. So this is how we find the fourth roots of minus 1. We take the angle of minus 1, which is pi. We divide it by 4. We get pi over 4. And since the modulus of minus 1 is plus 1, we take circle of radius 1. We take the angle pi over 4, look at where it intersects the circle. It gives us the first root. And then keep adding pi over 2. Why pi over 2? Because the complete revolution, complete circle, gives us the angle 2 pi. We are looking for the fourth root, so we divide 2 pi by 4 to get pi over 2. And every time we add a pi over 2. So all of these are right angles, pi over 2. So we get the four solutions. So to summarize, when we have lambda 4 equals minus 1, we get the solutions lambda 1 square root of 2 over 2 plus I times root 2 over 2. For lambda 2, and lambda 2, okay, minus root 2 over 2 plus I times root 2 over 2. And we get their conjugates, lambda 1 bar, lambda 2 bar. For we have polynomial of degree 4, so we have 4 roots. Now, I don't need to consider the conjugates, right? So for lambda 1, which is root 2 over 2 plus I times root 2 over 2, we have real solutions. Y1, which is e to the root 2 over 2 t cosine of root 2 over 2 t, and y2 e to the root 2 over 2 t sine of root 2 over 2 t. And for lambda 2, minus root 2 over 2 plus I times root 2 over 2, we have the real solutions, y3, which is e to the minus root 2 over 2 t cosine of root 2 over 2 t, and y4, e to the minus root 2 over 2 t sine of root 2 over 2 t. And finally, the general solution, C1 times Y1 plus C2 times Y2 plus C3 times Y3 plus C4 times Y4. Now, Y1 and Y2 are independent because in one of them we have the cosine and the other we have sine. Y3 and Y4 are independent with Y1 and Y2 because the coefficient in the exponential function are different. In Y1 and Y2, the coefficient of the exponential function e to the root 2 over 2, but for Y3 and Y4, the coefficient is minus root 3 over 2, minus root 2 over 2. So all of those functions are independent functions, although with a slight difference, but still that slight sign plus minus makes the whole difference. It gives us the four independent solutions of the differential equation. This example may look a little bit complicated. I included it here because I think you should see somewhere how to find roots of minus 1. You can use the same procedure for any root. So instead of the fourth root, you can consider the cube root or fifth root, sixth root, seventh root. But in that case, of course, the cosines and sines of the angles may not be so, you may not be able to write them exactly. So the fourth root may be the easiest case we can consider. You can consider taking the cube root of minus 1 using the same method. So instead of 4, you take 3. So the angle of minus 1 is still pi, but now you divide it by 3 to get pi over 3. And every time you add 2 pi over 3 to get the three solutions. Using the angles, sines and cosines, you can write the roots. So maybe as an exercise, find let's forget it. Okay. Just consider this. Try to understand how I worked out the example, but don't worry, you will not be asked to repeat the same computation yourself. As I said, I just wanted to include a case where you see how to find roots of minus 1. Okay, so that's all for this video. We will continue with more examples and the other cases. Well, basically, we have just one other case, repeated eigenvalue. But before that, I will try to solve some more examples of distinct eigenvalues, and then we will continue with the case of repeated eigenvalue. Okay, so until next time.